One of the most amazing features about tangent measures is the following result called tangent measures of tangent measures are tangent measures. And it's basically what it says on the tin. Suppose we have a radon measure mu, then at almost every point x in the support, and for every tangent measure nu at x, the following hold. So first of all, we have that every push forward of the tangent measure nu under one of our blow-up maps, TYR, so that means any translation or dilation of this tangent measure is also a tangent measure of mu at the point x. And in particular, recalling that tangent measures of nu are exactly limits of multiples of sequences of measures of this form, where we take a sequence of radii r as r goes to 0. What that tells us then is that the set of tangent measures of nu at any point y in its support is contained in the set of tangent measures of mu at the point x. We won't go through the proof of this, but we'll highlight what the easiest and hardest parts are. So first of all, as we just saw, 1 implies 2 clearly. So we just have to focus on part 1 of this theorem. Furthermore, if we just look at dilates of a tangent measure nu, so just dilates at the origin, then if our tangent measure nu is a limit of blowups of the following forms, Ci, Tx, Ri, push forward mu, then it can be shown that the push forward of nu under T0R is the same thing as the weak limit of T0R push forward this measure. And then we can pull out that number Ci, and then we can compose the dilation with the map Txri to get that this is the same thing as the weak limit of Ci times Txr times Ri push forward mu. And now, because this limit converges weakly, that means that all these limits here converge weakly as well to a measure. And thus, the limiting measure, which is T0 R nu, it will be a tangent measure of mu at the point x. So this means that the real meat of the proof is showing that translates of the measure, which are the same as pushing forward by maps of the form Ty1, where y is in the support of the measure nu. So the meat is in showing that for such maps, the push forward of nu is also a tangent measure. And this is a much harder thing to prove. In particular, notice that the above proof that dilates of a tangent measure are also tangent measures holds at any point x. So the case of translates requires some more measure theory, and that's why this result holds only at almost every point instead of at every point. So using this theorem, we can get more information about the structure of tangent measures of radon measures whose densities exist almost everywhere. So recall Marstrand's theorem that said that if we have a radon measure and its S densities exist almost everywhere, then S must be an integer. And recall that as part of the proof, we had to prove the following lemma, that if we have a S uniform measure in Rn whose support is not equal to all of Rn, then this S uniform measure has a tangent measure that has a tangent measure supported in a n-1 dimensional subspace. So using this lemma, we end the TM theorem from the previous slide. We can get the following corollary, that if we have a radon measure in some Euclidean space whose m-dimensional densities are positive and finite almost everywhere, where m is an integer, then at almost every point, the set of tangent measures of mu at x contains a flat tangent measure, meaning that there exists some m-dimensional plane, so that Hausdorff measure restricted to this plane is one of the tangent measures of mu at the point x. So let's walk through the proof of this. So under the assumptions, the tangent measures are m uniform almost everywhere, as we saw when we proved Marstrand's theorem. Furthermore, the tangent measure of tangent measure of tangent measure theorem, the conclusions hold at mu almost every point x. So what we do first is we pick a point x such that the previous 2 bullet points are satisfied. So the tangent measures are all m uniform, and also the conclusions of the TM theorem hold. Okay, so let nu be a tangent measure of mu at x. So we know that nu is an m uniform measure. Since m is an integer strictly less than n, this implies that the support of mu is not equal to all of Rn, and this was something that we saw as well in the proof of Marstrand's theorem. So that means that by the lemma from Marstrand's theorem, we have that Nu has a tangent measure lambda, which itself has a tangent measure omega, supported in a n-1 dimensional plane, which will denote Vn-1. Now, because the conclusions of the TM theorem hold, that means that lambda must be a tangent measure of mu at x. But also, again, by the TM theorem, since omega is a tangent measure of lambda, now it itself is a tangent measure of mu at x as well. And now we continue. So omega, if m is strictly less than n-1, then the earlier lemma implies that omega has a m-uniform tangent measure of some tangent measure that has support contained in a n-2 dimensional subspace. And then by the above arguments again, that tangent measure is also a tangent measure of mu, and thus we've shown that mu has a tangent measure that is m-uniform supported in a n-2 dimensional subspace. And then we just keep going and going until we finally arrive at showing that mu has a m-uniform tangent measure mu prime that's contained in a m-dimensional subspace V sub m. Now I claim that the support of mu prime is actually equal to all of this m-dimensional subspace. And the reason why is that if the support were not equal to all of this subspace, then that means, again, I can apply the earlier lemma to show that this uniform measure has a tangent measure of a tangent measure supported in a m-1 dimensional subspace. But that's impossible, because then I will have a m-uniform measure, and hence a m-Frossman measure supported in a m-1 dimensional plane, which is impossible. So thus the support of mu prime must equal all of Vm. And then this implies that the measure mu prime must actually be a constant times Hausdorff measure restricted to this plane. And you can conclude this by, for example, using some of the conclusions from the material on derivatives of measures that we discussed earlier in the class.